Okay, so we're going to pick up where we left off. I am done doing unsigned numbers like above, and so we're going to move on to the next part of the exercise where we start computing two's complement for binary and decimal and hexadecimal numbers. As a first thing to kind of help get oriented, well, some of the point of two's complement is to be able to represent negative numbers. So you can see that here in this row, in this example, the leftmost bit is a 1, and therefore that's going to be a negative number, right? So the leftmost bit you can almost regard as kind of encoding whether your given number is negative or not. So if it's a 0, it's not negative. If it's a 1, it is negative. Uh, and effectively what that does is it basically means that half of the numbers that you represent are going to be negative numbers, right? So half the numbers are going to lead with a 0, the other half are going to lead with a 1s. So half of them are negative and the other half are non-negative. I wouldn't say the other half is positive because 0 is not a positive number. So there is one number that's neither negative nor positive. But anyway, so but we can say that half are negative, half are non-negative. So so that's one useful thing to start thinking about to get familiar with two's complement. Now, for another thing, this is kind of a, so to speak, famous two's complement number. And the reason is because, well, this represents -1, right? So no matter how many bits you have reserved to start playing with two's complement, if you make a number of all ones with however many bits you have available, that's always going to be what represents the number 1, or -1, sorry. And one way that you can see this is, one thing that I like to see to help me to understand how two's complement works and why it represents what it represents is to say, well, look, if you took this number and you add 1 to it, what would happen? Well, if you add 1, +1, so all zeros until the rightmost digit is a 1, maybe I can simulate that down here. So let's go ahead and make another section for uh, two's complement. And just as a little explainer, if we had 1, 2, 3, 4, 1, 2, 3, 4, right, a block of all ones, and then I do 1, 2, 3, 4, 1, 2, 3, 1, right? So this number underneath is the representation for the number 1. Um, what happens if I add these numbers together, right? And if I add these numbers together, right, the hope here is that with an appropriate definition of addition, that the top row, I'm hoping to convince you, is -1. The second row is, I think, know is +1. And so how do we see that the top row is -1? Well, you should have that if you add -1 to +1, you should get 0. So I'm hoping to demonstrate that by adding these two numbers together, you get 0 and convince you, right? So the goal here is to convince you that this block of all, or right, this number composed of all bits set equal to 1 always represents -1. And so if you add 1 to it, we should get 0. How do we see that? Well, the rightmost bit, I'm going to have to type this with my first entry being the rightmost bit. So just kind of know that eventually this bit is going to land in the rightmost column. But anyway, so if you do 1 + 1, you get 2, but of course, because we're working in binary numbers, you have to, right, there you don't have a symbol for the number 2, so you simply write a 0 and carry the 1, right? So a 1 is going to carry over here, but otherwise I write a 0 for the bit that's going to go underneath this rightmost column. Now you move over to the second column and you have a carried 1. It's kind of invisible here, but we know that we are carrying a 1 into this column. We have a 1 and then a 0. So ultimately, the same process happens, right? You write a 0, carry the 1. In the next column, you write a 0 because, right, again, you're going to have 1 + 1. So you write a 0, carry the 1. Do it again and again and again. And it's going to happen. Now, you know that there's going to be this like final carry way off to the left, but in general, we are going to regard those kinds of carries as simply being truncated. So, so that's the system of arithmetic that we do when we have, basically a finite number of, memory addresses or bits. Is, when you have a carry, at some point, right? Like since the computer is finite, you're gonna have to run out of space eventually. And so, at least in this relatively small case, we'll just go ahead and say that when we run out of space, the carry bit just gets thrown away. And indeed, you get the number 0, right? So in this system of arithmetic that's kind of constrained to all the numbers that you can represent with just these bits, indeed, the top row plus the bottom row works out to 0, so there must be negatives of each other. And since we know that the bottom is 1, then the top is -1. So, okay, so that's one way to understand that this number made of all ones is always going to represent -1 for whatever number of bits you have doing 2's complement. It's also worth thinking of it from a slightly different perspective, which is that we know that we have, like, let's actually do this from a small example so that we can really see what's going on in a fairly manageable way. So let's talk about 2-bit numbers, right? So our 2-bit numbers are going to be these. And we are trying to use these numbers to represent integers. And of course, we can only represent 4 of them, right? 2 to the 2, 4. So we only have the capacity, if we're using 2 bits, to represent 4 different numbers. So the intent here is that we would basically make a window, right? And we want to represent negative numbers, right? Again, that's part of the point of 2's complement, is that, sort of part of the mission is to have a representation of some of the negative numbers. And so, how do we do it? Well, intuitively, right, it would be weird if 0, 0 didn't represent the number 0. And of course, we're going to have 0, 1 represent the number 1. But already we've used up half of the numbers. So I should probably write this as 0 and pad it out with a 1, right? Because these are my decimal values. And so when you get to, right, when you've exhausted half of the numbers, then you should wrap around to the other sort of side of your available decimal numbers. And so this should represent -2, right? Because we know that we're going to, if we know that we have 4 numbers that we can represent, half of them are going to be negative, then we know that we're going to have 2 negative numbers, and so the least negative number will be -2. And then as we continue incrementing these numbers, they keep getting bigger and bigger. And indeed, you can kind of see that, okay, so as we increment from -2 to -1, we just add 1, right? So that actually just totally aligns with what kind of makes sense, that if you took -2 plus 1, you would get -1, right? So that's why adding 1 gets you this larger number, right? Less negative, but larger in a sort of absolute sense, basically. So anyway, and so hopefully that kind of demonstrates, in a relatively small and manageable case, what's going on. Let's do it again, just with 3 bits, right? Just in case this exercise is of any use, and right, you want to see it just kind of, confirm that these patterns continue as you add more bits. So we would have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and then 1, 0, 0, 1, 1, 0, or sorry, 1, 0, 1, and 1, 1, 0, and 1, 1, 1. Right. Okay. So we have 8 numbers represented, which, right, 2 to the 3 is 8. So this is the right quantity of symbols, I guess you could say, or quantity of numbers to write out. And again, right, so going through it again, this is going to be our number 0. This is going to be 1. This is going to be 2. And this is going to be 3. And we've already now used up half of the available symbols, right? If there are 8 symbols total, I've just used up 4, right? The number is 0 to 4 minus 1, right? So those are the sort of first half of non-negative numbers. So now I start up with the negative numbers. We know they'll start at -4, and as you increment, you'll get closer and closer to 0 from the other side, because they're kind of wrapping around. Indeed, right, -4, -3, -2, -1, and if you added one more, then all the bits would flip to 0, which and you'd throw away the carry, which would land you back at 0. So it all makes sense, I hope. I hope that makes sense to you. Anyway, so that is the sort of concept behind two's complement. And so hopefully, when I say that there are sort of these two's complement numbers that are really worth knowing fairly well, which is this one, because this is your most negative number, right? It is your extremely negative number, and it is 2 to the 8 divided by 2, so 2 to the 7, but made negative, right? Because it's so it's the most negative number that you could have, and 2 to the 7, we computed that earlier. That was 128. So again, right? So a so to speak famous two's complement number is a leading one followed by all zeros, and that is however many bits you have. So in this case, 8 bits. Take 2 to the number of bits minus 1, right? So that's in this example 2 to the 7. And that is sort of the absolute value of the most negative number. I should have a negative sign here. So 2 to the 7, right? That's 2 to the number of bits minus 1. That is, in absolute value, the most negative number that you could have. And so we stick a negative number on the front to represent this most negative number that you could have. And then if you add on to it, it keeps getting bigger and bigger, which is to say closer and closer to 0. And that means that by the time you get to this block of, or this number composed of only bits equal to 1, that you've got your least negative number right before 0. All of that is, of course, a description of -1. So these, right, I just kind of regard these as just as kind of orienting things, how I think, right, how I try to stay oriented when thinking about what numbers are represented in two's complement. Okay, so hopefully that's just a fairly sensible overview of two's complement. Okay, let's look at, like, if we did have a number like here, right? So we have this number represented in binary, and we would like to translate it into its decimal form. How are we going to do that, right? You don't want to like count through all of, right? You don't want to like write out these sequences of binary numbers, and right, like these sort of more manual ways of trying to do it and understand it are painful. So there's a nice sort of algorithm for how to find two's complement. No surprise, it depends on whether or not the leftmost bit is equal to 1. If the leftmost bit is equal to 0, then you simply do what we've already done. On the other hand, if the leftmost bit is equal to 1, then we simply write down the minus sign, right? We already know, because that leftmost bit is a negative, we can simply write down the minus sign. And then, having written the minus sign, we would love to have a way of taking a number and finding its negative, right? Because in this case, if we could do that, if we could take this binary number, find its negative, well, then that must represent the positive version of the number, and then we already know how to find the positive version of the number. Uh, so let's do that. What's the algorithm, right? So right now the question is, what is the algorithm to find the negative of this number? And the answer is, and by the way, like let's maybe sort of test this idea out on a more sort of familiar and simpler example like this one right here. We know that this number composed of only ones is -1. And so how do we find its negative? Well, you want to find the number which, if you added them together, you would get 0, right? And so how are we going to find the number which, if you added the number, of all ones, every bit equal to 1, that plus what should equal 0, right? That's how we're going to find this, the negative of this number. And you say, okay, well, if I want this to be 0, then let me maybe, write that the rightmost bit should be a 1. And we know that the rightmost bit must be a 1, because if that rightmost bit is a 1, then the 1 plus the 1 is going to equal, or have at least in this position, right, in the rightmost column, we'll have a bit equal to 0, and then we'll have a 1 that carries over, and we'll try to fix that and manage that later. But at least for now, I want to like 0 out that bit. And so I write a 1 in this number that I'm trying to build as its negative, so that when they add, the bit that is in this column is equal to 0. Okay, well, now that I've added a 1 there, a 1 carries over to the next column. And so then they're going to add, turn into 0. And actually, I don't have to do any, right? Like, it's already a 0 if I just let the carrying do this for me, right? And then that's going to cause another carry and another carry. And we've kind of seen a similar thing before, where all of these carries kind of run off to the other, to the left side, and then the final carry gets thrown away. So, so this is the negative, right? This is how we find the negative of the given number. And it's really kind of conspicuous, right? Because it's almost all zeros except for the rightmost one. Well, that's actually kind of always how this goes, right? In fact, this is the algorithm, is if you take any number and you want to find its negative, then you simply flip every single bit and then add 1 at the end, right? So if I wanted to, for instance, well, I guess we'll just go to the example over here, this 1111, 0110, right? So let's find so down here, let's find the negative of this number. Well, I claim that we'll find it if we flip all the bits. So let's do that first. So I get, step 1 is flip all the bits, 000, 1001, right? So I flipped all the bits. And then I add 1. And so I get 0000, 1010, right? So if I add a 1, then that's going to add here. I carry the 0 down, or the bit that gets saved in this column is 0 after adding 1. And then a 1 carries over to the next column, and because in that next column there's a 0 here, and I'm only adding the number 1, so so actually maybe it helps if I wrote this out as So we're adding these two numbers, right? That's the idea here. And so in the far right digit, right, 1 and 1, the digit that gets stored in this column is a 0. A 1 carries over to the next column. Otherwise, you have 0 and 0. So ultimately, you are left with a 1 in this place. And then zeros, 1s, 0, 0, 0, so on, right? Okay. So my claim is that this number is the negative of this number. And you can test it out, right? There's a nice test that if you add these two numbers together, they should zero each other out entirely. And you could go ahead, take that number plus this number, and when you add them together, you should find that indeed, after doing all the carries and throwing away that last leftmost carry, that in fact the whole thing turns into zero. So indeed, this is the negative of the number. And then the question is, well, what is this number, right? So again, remember that what we're even doing in the first place is taking this binary number and writing down its decimal representation. We already decided that it's going to have a negative sign, and now we've found the negative of the number. We can go ahead and find it as a decimal. So what is this number as a decimal? Well, in fact, it's actually the same as this thing up here. So we've already gone through the process in the earlier video of finding that this has decimal expression as the number 10, right? So so effectively, right, so I've basically just gone through the whole procedure of showing you that this binary number turns into negative 10, right? And as a summary of the procedure, how do we do it? We say, well, the leftmost bit is a 1, and therefore it's negative. Now let's find the negative of this 2's complement number by flipping all the bits, adding 1. You get this. This is the negative of the number. So it now is the positive, right? Because you're taking a negative of a negative, so it's now positive. And then, and that gives, right? And then you just translate that into decimal to find what number goes underneath the minus sign. So that's how you find the decimal representation of a binary number written in 2's complement. Okay. How do you find the hexadecimal version of a number written in 2's complement? Well, it's exactly the same procedure, right? You just chunk it into blocks of 4. So this block of 4, what does that represent? Let's just do it like this. Let's say, well, the 2 to the 0 place is a 0, right? So there's going to be no contribution of the number 1. Then this is the 2 to the 1 place, and so that is 2 to the 1 is 2, so there's going to be a contribution of the number 2. Then there's going to be this 2 to the 4, which is the contribution, right? Or sorry, 2 to the 3, or sorry, 2 to the 2, which is the number 4. So so there's going to be a 4 plus a 2, and altogether there's a 6, right? So this leftmost block of 4 bits gets us this number 6. Okay. And then what about this block of all 1s? We've already seen that a block of all 1s gets translated as F, right? And if you wanted to sort of like work through that again, and we did this in the previous video, but the procedure was to convert that into decimal and then convert the decimal into its hex code. So that's that. Certainly, if we're going to next do this one, right, this block of all 0s would turn into a 0. This block of all 1s would again turn into an F. So in the second row, so let's do row 2, the hex part is going to be 0, right? We said a 0 in, yes, a 0 in the rightmost part and an F in the leftmost part. So that's the hex. And then for the decimal, let's come over here. Yes. And then if we want to come over here, we say, oh, right. Here we say, okay, so the leftmost bit is a 1. So we know that this is going to be a negative number. So let's go ahead and write that down. It's going to be negative. And then we're going to find its, right? So we're going to find the negative of this number. So let's go ahead and take that. So I'll just put that here. and say, okay, so if I'm going to take the negative, I'm going to flip all the bits, and then I'm going to add 1. And what does that get me? It's going to get me, right? You can kind of hopefully see where this is coming from, but it's going to turn into this, right? So there's the positive version of the number that I want, and this is relatively easy to understand what this is. So if you think like this is the 2 to the 0 place, this is the 2 to the 1 place, this is 2 to the 2, 3, this is 2 to the 4, right? So basically there's no contribution by anything else except 2 to the 4. So this is 2 to the 4, and therefore this is equal to 16. So this is negative 16, and there we have it, right? So we now know the decimal value that goes here, negative 16. Okay, let's do it again. Let's take this hex number, and since the leftmost thing is 0, then the left block is going to be all zeros. The right part is this F, so that's going to be a block of all 1s. And so in row number 3, we're going to have, what order did it go in? So all zeros and then a block of 1s. Okay, that is right, and that is the that's the binary. And then we want the decimal. And to convert to the decimal, we can see that the leftmost bit is a 0. Therefore, this is already a positive number. And so we don't need to do that conversion. We merely take this number and write it down as a right, like convert this binary into decimal, right, in the unsigned way, if you like. Notice, by the way, that this is basically, right, I'm now finding shortcuts, right? I don't want to go through the official procedure every single time because it can sometimes be long. One nice way to see what this is, well, look, it's just 1 shy of a 1 here followed by all zeros there. So since it's just 1 shy, I could go ahead and take that number, which we already know is 16, right? 2 to the 4, right? So if it was just a 1 here with all zeros, which is only 1 away, that would be 16. But since it is 1 less than that, then it's 16 minus 1, which is 15. So anyway, that's just a shortcut, not terribly important, but a nice quick way of computing what this is as a decimal number. So that's positive 15, and so what goes here is positive 15, which, by the way, I guess should remark that that makes total sense because we already know that F is the number 15, so this is basically 15 with a block of zeros to the left. Notice, right, but it really is important that the 0 is here because that's going to tell me that it's a positive number. And by the way, I guess it's an interesting question. How do you just look at a hex number and decide whether or not the decimal is going to come out positive or negative, or or negative or non-negative, I guess I should say? Well, since our rule for the binary codes is that if there's a 1 in the leftmost bit, then it's going to be negative. Then let's think about what that kind of means for the hex code. Well, the leftmost bit is this or anything bigger. That is going to tell you that it's a negative decimal, or really a negative number. And so what is this number? Well, that is 2 to the 3, so 8, right? And so so what this is saying is that if your hex code, right, if your leftmost hex code is 8 or more, then it's going to be a negative number. If it is less than 8, right, if it is 0 through 6, or sorry, 0 through 7, then it'll be a non-negative number. So for instance, right here, my leftmost digit, my leftmost hex digit is A. A represents 10. 10 is bigger than 8, and therefore I know that this is going to come out to be a negative number. Now, of course, right, since we need to build the binary first anyway, we might as well figure out what the binary is and then translate the binary into decimal. It's the kind of most sensible, I think, way of doing it, but we can at least predict right away that this hex is going to be a negative number. Maybe, should we do any of these others? I don't know. I think this video is already kind of long for such a basic concept, so maybe this is enough. Let's quit here.